Hi, I'd like, in the spirit of the previous videos with the four-cycle engine and the rotary engine, I'd like to present something to do with the Carnot engine cycle. And I'm sorry, this is probably going to be somewhat incomplete, because there are some things that I haven't gone through the derivations of yet, and some things that still kind of confuse me. But before I begin talking about the Carnot engine cycle, I'm going to talk about isothermal processes. And these are processes where delta T is equal to 0. There's no change in temperature in these processes. And there's basically there are only a couple examples that I can think of myself. There's melting and freezing. There's condensation and vaporization. And then there's one other one that I can think of, where you have a balloon floating up to the surface of water, or an air bubble floating up to the surface of water. If you have the water at constant pressure, constant temperature, but the pressure below is, you got the high pressure below and the low pressure above, then the volume of the balloon is going to increase, and the pressure, so the volume goes up, delta V is greater than 0, and the pressure goes down, so delta P is less than 0. But here's the interesting thing. The heat, which is generally, we've been talking about it being N times a specific heat times delta T. Well, this delta T is not changing. There's no change in temperature. So this can't be. First of all, there's not going to be any change in internal energy in the gas, because the internal energy of the gas is a function of the velocity of the molecules, and that includes the linear velocity, the rotational velocity, and the vibrational velocity. But if that temperature is not changing, then that velocity of the molecules is not changing. So that means that there is no heat exchange, at least by our previous definitions of heat. So what's changed? The balloon is rising, so that means there is going to be a gravitational potential exchange. The gravitational potential of the balloon will go up, and the gravitational potential of the water around it will go down. And so there is an energy release into the system, and the total of that is probably going to be the buoyant force times the distance, and I'm trying to remember a formula for the buoyant force. It's basically the force of gravity, which is mass times gravity, except the mass is going to be like rho times the volume. Think of it as rho v minus rho v g, where rho is the density of the air and the density of the water, and that would give you an idea of how much energy was available, because we'll multiply that by the height that it travels, and that's going to give us an idea of how much non-heat energy is available. And let me be more specific. When I say non-heat energy, I mean non-temp changing energy. Now the question I ask is, will this show up in the first law of thermodynamics? Recall that the first law of thermodynamics says that if you add heat to a system, that heat will show up as either a change in the internal energy of the gas or work done on the environment. In this case, yes, we do have work done on the environment because that volume is changing. And but we do not have any change in internal energy because the gas is still moving at the same velocity. But This Q that we use over here is basically a non-heat energy. It doesn't change the temperature of the gas. It's going to be coming from this buoyant force over here, or possibly just a portion of this buoyant force, because part of that buoyant force is of course going to cause acceleration of the balloon upward. Alright, I'm going to stop that for now because that's probably about as clear as I've ever presented this information, and maybe later I'll move forward from that point. But for now, let's just come back here and start talking about the Carnot Engine cycle. The Carnot Engine cycle is a set of 4 processes, and on a pressure versus volume curve, it looks something like this. And the arrows go clockwise around this, and I drew that curve very badly. Let's do that again. Okay, and we've got 4 parts of it, and the top and bottom ones are isothermal, and the left and right ones are adiabatic. Now, adiabatic is a very simple, more or less familiar concept. It's just what you get from a fast expansion of a gas or a fast compression of a gas. The limiting equation of an adiabatic equation is Q equals 0. You're not adding or subtracting heat from the gas, from the external, well, I guess from anywhere. It's insulated, and there's no changes in chemical potential, so there's no ignition or anything like that. Nothing is changing from one kind of gas to another kind of gas or anything. Okay, on the other hand, isothermal, the governing limitation behind this is that the change in temperature is 0. And I've been discussing that in the first half of this video, so I'm going to try to draw a diagram. Well, let me see if I can find the one from the book first. Here's what they have in the book. They have an isothermal expansion, followed by an adiabatic expansion, followed by an isothermal compression, followed by an adiabatic compression. That goes along with that this diagram up here. This is the isothermal expansion. Notice volume is increasing. The adiabatic expansion, still volume is increasing. And the isothermal compression and adiabatic compression. Now, work is done on the environment at high pressure here in the isothermal thing, and then in the adiabatic thing process, isothermal process and adiabatic process. Then the environment does work on the gas here in the isothermal process compression and the adiabatic compression, but it does it at lower pressure. So this is going to be, it does more work here and less work here. Now, why is this considered an ideal engine? Why is it that that they say no engine can ever be more efficient than this one? Well, for one thing, they say that these processes are entirely reversible. So, for instance, the adiabatic, you let the gas expand and then compress it again, and it will go back to exactly the same state. With the isothermal, if you let the balloon go up and you force the balloon down, it goes back to exactly the same state. I think there is some more convincing argument to make the case that that this is the best efficiency that you can achieve. I'm going to have to review some to remind myself exactly why that is the case. In the meantime, I'd like to present a slightly different diagram of this, just to kind of make it more similar to the other engine animations that we've seen. And the main thing I'm going to do is change this so that instead of having to remove this energy reservoir and then replace the energy reservoir, I'm going to set it up so that So let's say I'll draw a circle, and how about another circle around that. Imagine that over here we've got our hot reservoir, and over here we've got our cold reservoir, and then these two areas are going to be perfectly insulated. And then, like in our 4-cycle engine, we're going to present it as though we have 4 pistons moving around. And then somehow this is doing isothermal expansion, and this cylinder is doing adiabatic expansion, and those two working together are performing the power stroke. And the cylinders over on this side are expanding, while this cylinder is going through isothermal compression, and this cylinder is going through adiabatic compression. And so these two are being forced to compress. Basically, these are providing the power. These are actually absorbing power. These 4 cylinders are all going to be attached somehow, so that these are doing the pushing, and creating the force, while these are absorbing the work, but not as much work as these are producing. Now, the efficiency of a Carnot engine is E equals 1 minus the cold temperature divided by the hot temperature. So that's the ratio of the temperature over here divided by the temperature over here. And that has to be in Kelvin. So if you had the isothermal compression happen at 0 Kelvin, and it compressed all the way, and the gas compressed all the way to 0, you could get, theoretically, I guess, 100% efficiency, because it would be 1 minus 0 over whatever temperature you wanted whatever temperature you had the hot side at, which really doesn't matter. It would just be 1 regardless. Now, I'm going to just start saying some things that might not make sense, but maybe I'll be able to make sense of them later if I watch this again. But basically, the entropy gained by the gas in the compression and expansion during the isothermal compression and isothermal expansion, the entropy gained by the gas here could be converted almost or nearly entirely into work here. The only way you're going to get down to 0 Kelvin in an adiabatic expansion is if you let the gas expand for probably an infinite period of time. Just let it, expand into space towards infinity, and eventually you will have 0 temperature, and then you could compress it from that 0 temperature. Okay, and then start the process over again. Let it expand. So I don't have any idea. Let's just say something crazy that maybe this here, the adiabatic expansion, is the Big Bang. The adiabatic compression is a black hole, and then you've got the isothermal expansion, while the entire universe is bathed in the cosmic microwave background radiation, and then the isothermal compression as particles go, as particles enter the event horizon of a black hole and move in, something like that. And, well, that would give us a perfectly efficient energy cycle. Of course, there wouldn't be any information remaining from one cycle to the next. One little detail I wanted to mention, it might be better to imagine this thing following a curve around the side. So you can imagine this being shaped for the cylinder to expand on, and this continuing to shape based on the adiabatic curve. And then when it gets over here, you have it shaped so that it's so that the cylinder is being compressed, is being forced to compress by things. So you could shape the walls of this engine so that the cylinders are pushing outward on the expanding parts and are being forced smaller on the compression phase. And honestly, that stuff that I was saying about the Big Bang and black holes, take that with a huge grain of salt, because I am just kind of letting my creativity run free there. But, you know, if on the odd chance I said something that was accurate, then, you know, you might have a eureka moment, or and it might either remind you of something you were thinking later, or inspire you to be more interested in the subject.